In this video, we'll be talking about 3 by 3 Jacobians, and we're solving for the determinant of the Jacobian, and just a little review. Jacobian is something that is, I guess, a number or some values that take into account a transformation. So when you're turning the rectangular coordinate system into another coordinate system. And rectangular coordinate system is just the x, y, and z values into another coordinate system like spherical coordinates. And today we're actually going to be using spherical coordinates as our Jacobian. It's going to be a very long trigonometric process, but you know, if you can push through and you can watch the entire proof, I guess, video, then you'll know how to solve for Jacobians. But most Jacobians aren't going to be this complicated. After a certain point, after I show you how to set it up or solve for the determinant of the 3 by 3 matrix, I'd recommend just you don't even have to watch the rest of the video. Like, you don't need to know how to fully adjust everything. Let's go ahead and begin and end the yapping. So whenever you're solving for Jacobian, you want to write your transformation factors. So you have rho of sine of theta in spherical coordinates. I mean sine of phi and cosine of theta is equal to x. Also rho of sine phi sine theta is equal to y, and rho of cosine phi is equal to your z value. And now we have to set up a Jacobian. So Jacobian is set up like so. You have some, let's actually write that later. You have some partial derivatives all in a 3 by 3 matrix. And don't let like the matrix name scare you. Matrices are genuinely not that hard to learn. And for this, all you need is the determinant, so you don't have to learn everything about them. So you want to set up your Jacobian matrix like so. And the matter in which, the order, actually, in which you write these partial derivatives matter less than you think. You don't have to write it exactly like I do. But there's a couple general rules that you have to follow. And these two general rules are stated like so. So the general rule is you have to assign each row, so across, with some function, one of your old functions, right? So x, right, is assigned all in a row. Your top variables must all be the same in a row, and your bottom variables must all be the same in a certain column of these partial derivative notation. And if you have, like, if you want to switch x or y here, you want to switch the placement of these, doesn't matter. As long as you solve the determinant properly, you'll still get the same answer in the end. So don't worry about that too much. Just make sure that your rows are assigned to specific old variables like x, and your columns are assigned to specific new variables like rho in this case, or the variables you're transforming into. And these is partial derivative notation. So what this stands for, if you need a quick review, is this is the partial derivative of x with respect to rho. So the top variable is your function value, and the bottom variable is whatever you're partial differentiating to, partial differentiating with respect to. Sorry. So with respect to rho of our x, we have sine of phi, cosine of theta. With respect to theta, we have rho sine of phi, negative sine of theta. And with respect to phi, we have rho cosine of phi, cosine of theta. How about for our y values? Well, y is, with respect to rho, is sine of phi, sine of theta. Y with respect to theta is rho sine phi, cosine theta. And rho and y with respect to phi is rho cosine phi, sine of theta. How about for x? Actually, wait, we can actually make this smaller. Saves a lot of space for us. And for our z values, I'll just breeze through this. So this is cosine of phi, 0, because our z function is not dependent on any theta values. And with respect to phi is negative rho sine of phi. And this is our Jacobian matrix specifically for our spherical coordinates. Now we have to solve for the determinant of this matrix. I'm going to show you how to do that right now. Now, how do you actually solve for the determinant of some 3x3 matrix? A 2x2 matrix, it's a lot easier, but a 3x3 matrix, man, it's so tedious. So I'll just show you how to set it up and continue on with the, algebraic trigonometric manipulation. So what do you have to do first? Well, I'm going to be finding the determinant across the top row, left to right. What do I mean by that? Well, I'm going to start off with this value here. I'm going to cancel out this row and cancel out the column that this value is in. Then, like so, we're going to multiply. We're just going to write down the value that we're talking about right now at the top, which is sine of phi, cosine of theta. And we're going to multiply it by the determinant that actually is left over when you cross everything out. So the term that's left over is this guy right here. Or the new matrix, actually. Sorry. The determinant of this new matrix. So let's write down that new matrix. So that new matrix is rho sine of phi, cosine theta, and rho cosine phi, sine theta. And also 0 and negative rho sine of phi. I gotta make these lines straighter. Alright. What's next after this? After this, subtract. And then when you subtract, again, you picked, remember what I said about the top row from left to right? Well, the next thing on the top row, next thing on the top row is negative rho sine phi, sine of theta. So we're actually multiplying, again, we write down rho sine phi, sine of theta, by a new determinant. And this determinant is going to be a little more tricky than the other ones because the way I solve it is going to be a little different than the way that your teacher or math textbook might solve it. And the reason why I solve it like this is because it makes your subtraction a lot more simple in the end. It actually might be little, maybe math teachers might not like me for solving it this way, but this is the way that I solve it from me being a student of Calculus 3 literally just a day ago. Like I took the final like 2 days ago. So this new determinant that we're actually multiplying our original value by, let's call this the OG value, is this matrix right here. So I actually went to the right first. So I'm starting off with the right of whatever I cross off. So whenever I cross off a column, I look to the right of that column, and that's my new matrix. So the new matrix is like so. P, or rho, cosine of phi, sine of theta, and sine of phi, sine of theta. And negative rho, sine of phi, and also cosine of phi. Okay, we have another part of our tedious step towards solving this. Let's make this smaller as well, if that one's going to be that small. Alright, now we subtract again. Sorry, we actually add everything. My fault. That's why the math teachers might not like me for that. The way I do it makes it so you don't have to subtract, you just have to add. I knew something looked off. But just add everything together whenever you're solving for your determinant in this case. And then now, again, from left to right on the top row, our next OG function will be this guy right here. And we cross off the row and the column, and we're left with this matrix. So remember what I said about looking to the right of the column we cross off. Well, if you look to the right of the column we cross off, there's nothing. Right? So this is the column we crossed off. There's nothing to the right. But we can actually, I don't know, maybe make a portal into another realm and then come to this side. So that's what's going to start our matrix. Let's multiply it together. So our original function is rho sine of phi cosine of theta multiplied by the determinant of our new matrix, sine of phi, sine of theta, rho sine of phi cosine theta, and cosine phi, and also 0. Now I know this is off the screen, but let me let's make this smaller so that you guys can see what I'm seeing as well right now. And all we have to do is set this entire thing up. Excuse me, together. Wow. This looks like a very, very long process, which it quite is, but let's go ahead and start it. So, what do we do first? Well, first thing I'm going to do is let's actually label this. Let's label our parts, our sections, so that you guys know what I'm going to be referring to when I refer to like number 1 or number 2. It's going to be number 1, this would be number 2, and this would be number 3. Each term is going to be their own number. The terms are things that are separated by these adding signs, addition signs. And we're going to solve for number 1 here. So the number 1 part is sine of phi times the cosine of theta times the determinant of this matrix. So how do you solve for the determinant of this matrix? Multiply across like this. So you multiply rho sine of phi by, so you multiply rho sine of phi cosine of theta by negative rho sine of theta, and you get negative rho squared sine squared of phi and cosine theta. And then next you subtract it by the next cross multiplication, which is just 0, because 0 times anything is just 0. So we leave this alone. And when we expand this, we get rho squared sine cubed of phi cosine squared of theta. Okay, let's solve for the second term now. Second term was negative rho sine phi sine of theta. Multiply by the determinant of this matrix right here. The determinant of this matrix, again, you cross multiply, and then you get rho cosine squared of phi sine of theta. Subtracted by the cross multiplication. Since there's a negative sign here, it also cancels out with this subtraction, so I'm going to turn this to addition. We get rho sine of phi squared times sine of theta. And let's simplify this further. We can make this significantly easier. This entire thing is equal to rho sine of theta. The reason why is because we can factor out rho sine of theta from both these terms here, and you get left off with cosine of squared phi plus sine squared of phi, and this is the trig identity that's equal to 1. So when you multiply your OG function with rho sine of theta, which is technically equivalent to this, you get negative rho squared sine phi sine theta squared. Okay, and then for your third part, you get, let's make some more space for each of these. Never mind, my handwriting is slanted, so I can't move it. So the third term is now rho sine of phi cosine of theta times the determinant of this matrix. So the determinant is, again, cross multiple. So we get 0 times something is always 0. So we get 0 minus the cross multiplication of these two functions, which is rho sine of phi cosine of theta cosine of phi. Heike, I cannot wait for the Demon Slayer movie, bro. I keep seeing TikToks on it. Man. For those of you guys that watch anime, shout out to you, because Demon Slayer is just amazing. You know, people say I'm a Demon Slayer glazer. I'm not gonna lie. I like the animation. I like the storyline. People say it's super basic. I'm gonna argue with you about that. But okay, let's go back to the problem. Multiply these two together. What do you get? You get rho squared sine squared of phi cosine squared of theta and cosine of phi. So again, now we solve for everything here. What do we do next? Hold up, guys. I kind of made a mistake. This is supposed to be cosine of rho cosine of phi. So therefore, this is actually cosine of phi right here. Let's go ahead and let's fix this. I'm gonna be honest. This is like the second take of this video, and I made the same exact mistake in the previous take, bro. This is like a fool me once, shame on you. Fool me twice, shame on me, bro. Whatever. I'll just keep going. That was just a mistake. Hopefully one of you guys caught that and were like scratching your heads, looking at me like I'm crazy. But let's just finish the rest of this problem. If you actually add everything together, all these terms, 1, 2, and 3, you get rho squared sine cubed of phi cosine squared of theta minus rho squared sine of phi sine squared of theta. Plus, actually, minus rho squared sine phi cosine squared theta cosine squared phi. Okay, we wrote everything down. Now let's just take this step by step so I don't make some like dumb error again. What you can do here, you can actually factor out rho squared sine phi, and hey, that looks like already our Jacobian for spherical coordinates. And then you actually get, in the end, you get sine squared phi cosine squared theta plus sine squared theta plus cosine squared theta cosine squared phi. So this is after I factor out negative rho squared sine of theta. And then let's ignore this for now. Let's save this. Let's save this with the green the green box. Green box. All right, and let's look at this guy right here. Oh, what can we do to algebraically manipulate this, or trigonometrically? Sorry, manipulate this so that you get some one value, I guess. Well, you can actually switch around your terms so that, let's actually write that down. Let's switch this around. Let's switch this, and let's put this after. So we just switched our terms a little bit. Didn't change anything about the function. And then we can factor out cosine squared of theta from the beginning, from the first two terms, to get sine phi plus cosine squared phi plus sine squared theta. This is the trig identity of 1, so you can actually cross this off. Wait, redo that. And then you have 1 times cosine squared theta, which is just equal to cosine squared theta. And you're left off with cosine squared theta and sine squared theta, which is, again, trig identity of 1. So actually everything in this, let's write with color. Everything in this section is equal to 1. So this actually kind of cancels out, because when you multiply 1 by something, it always stays the same. So our answer is technically just negative rho squared sine of phi. Now something looks a little bit off because your Jacobian is positive when you're doing spherical coordinates, but since we're solving for some volume element of an integral, we are going to set this to, we're going to find the absolute value of our Jacobian. Now if you solve this in another way, you'll probably get some positive number. If you solve for another way, you might get this negative of r rho squared sine of phi Jacobian. But this is basically just, like, I guess, kind of the proof for why your Jacobian for spherical coordinates is equal to rho squared sine phi. So if you have any questions, put it down in the comment section. Hope you guys learned something. I'm going to go eat wacky right now.